science, it's all about precision. Okay, and I gave you a fairly vague assignment, and you could, you were sort of, some of you were sort of sloppy about that, because the websites you used were sort of sloppy. And I know I asked you not to use the website, but I bet almost everybody did, or a textbook, didn't you? I mean, I could tell by your language choices. And there was one site that was commonly used, and I could tell it was commonly used because the organization of the comments was precisely the same order. So I'm not exactly sure, I didn't take any time to look at what that might have been. Okay? But as you move into writing for a scientific community, your language and your composition has to become more precise. And this is a good time to start that. So here are the precision rules. And so as I wrote this down on my notebook, and then I went away for a while and came back, and I thought, precision rules, it sounds like the noun, a sentence, a noun and a verb. And I thought, no, it works either way. The rules of precision or precision rules, with rules being a verb. Okay. So I want to minimize the use of pronouns. For example, don't use it. As much as possible, avoid using the word it. And this becomes really important on tests when you use it or they, and I have no idea what it means to you, okay? And if you use it in such a way that it's not clear what it is, I can assume whatever I want, okay? As a reader, I will assume whatever I want. And you're not going to like what I'm going to assume. So don't use it if you can help it. I would much prefer you using the same word over and over again so it is clear to me that you know what you're talking about. Okay? So they is not a good word. That is not a good word. Okay? The sentence that came to mind was, that really sucks. But you don't know what that is. And you know what it is, but the reader doesn't know what it is. Okay? Or this causes problems. Well, what is this? I don't know what I don't know if you know what's causing problems. You just said this causes problems, and so instead of using these words, tell me what this is, or tell me what that is, or tell me what it is, or they are. Okay? So choose your minimize your use of pronouns. And this is a good suggestion for the test. So test number 1, I usually let pronouns slip. At test number 2, I assume that if you don't tell me what it is that is upregulated, or tell me what it is that gets downregulated, I'm going to put in whatever I want. Okay? Choose your nouns carefully. This is a big part of precision. Okay? So this weekend, because I do this every weekend, I wash my socks in the house. Okay? That's essentially correct, isn't it? But I just didn't open up the door and throw my socks in the house. Where did I wash my socks? In the wash machine. But it is in the house. So a lot of times you use the word body. And it's just like me saying I wash my socks in the house. I also baked a cake in the house. Well, I didn't bake a cake this weekend. I made stew. I cooked stew in the house. Okay? So this continues to be a problem. Body and cells are not interchangeable nouns. A body is a body, and bodies are made up of cells. Okay, but the body doesn't take up glucose. Okay, cells take up glucose. Okay, I will be hounding you with this for the rest of the semester because you're going to be doing this for the rest of the semester. You're going to be baking your cakes in the house and washing your socks in the house all semester long. And I'll have to keep reminding you that. The other thing that you will certainly do is use cell as if it was an appropriate term for anything, like glucose or a protein. You know, insulin is not a cell, for example. I'm not sure if anybody made that particular mistake, but there are people who are using cell incorrectly, and you will do it again. I guarantee you will do it again, because that's the whole part of learning how to write, is you make the same mistakes over and over. So cell is not a protein, and we didn't come to this problem, but it will come. This is going to be the three things. Oh, a gene is not a protein, and a protein is not a gene. And I think probably 100% of you will get those two terms mixed up. And of course, I know you know better than that, but it's just going to happen that you're going to not distinguish between a gene and a protein, or identify a gene as a protein or a protein as a gene. It's going to happen. Okay? So now you have to start thinking about your words carefully. Okay? And this is a good time to start. And you're not going to master this like in the first assignment. This takes a while to master. Okay, here's another one. Be specific about effects. Okay, and I do see this in literature too. So I'm reading Nature Reviews Genetics, some article from Nature Reviews Genetics, Nature Reviews Cancer. I oftentimes see this particular problem. And I mean, for example, insulin affects blood sugar. That doesn't tell you much. Or glucagon affects blood sugar. That doesn't tell you much. You could say, you can make any comment, let's see, high LDLs affect your heart. That doesn't tell you a whole lot. So you need to be specific. Insulin lowers blood sugar. That's the effect. So if you can be precise about the effect, make sure you are. And I understand that you're going to be reading papers in which the effect is not specific, but extremely vague, and I think you might be frustrated by that. Okay, so so you will understand that frustration as a reader. So you got to remember that frustration when you're in the writing, when you're the writer. Okay. Also, there are a lot of vague phrases too. So avoid vague phrases. And you'll get better at this. So take a look at, and if I wrote the question, how so, or such as, that was because you wrote a vague phrase. Okay, so people have to eat better in order to avoid type 2 diabetes. People have to eat correctly. Oh, I don't know what that means. Okay, for me, eating better is having a Butterfinger Blizzard every single day. That's good eating. But that's probably not going to avoid type 2 diabetes. It may not lead to type 2 diabetes, but certainly not going to be preventative. Okay. Let's see. Other serious issues. A lot of times he said, here are some side effects of type 2 diabetes, and some of you said there are other issues such as. So take a look at your paper and I said, how so or such as. And from now on, think about, can you add that detail? If you can add the detail, do. If the detail helps demonstrate your point that you're making, certainly add it. If it doesn't help demonstrate the point you're making, I wouldn't. You know, we got to start sorting out when is detail important and when is detail just filling pages. Okay, so that's what I think it's going to be. What I'm going to be looking for next time is some precision, because the writing assignment is not going to require a tremendous amount of analysis, but it will require some describing in ways that are clear and concise, because you're writing to scientists now, but I think the websites you were looking at were not written for scientists. Would you guess that's true? If you look at like Wikipedia, or if you look at the Mayo Clinic guide or something, that most of the websites that I think you guys were using were not written for scientists, but now you're writing for scientists. There were some misgivings about diabetes. Some of the details we will be covering, because this unit we're going to be covering the glucose transporters and how they work. A lot of you mentioned GLUT4. Did you pick that up from physiology? Okay, you used your physiology textbook to get that information, or you all remember GLUT4 for some reason? You all remember GLUT4?
That's the one with the stress.
So at the end of this semester, you'll remember all those protein names? Yes, that's great. I know. No, right. Okay. But the use of it, I think about 4 people use the term GLUT4, which is a glucose transporter. And the implication was that all cells have GLUT4, use GLUT4. And that's not true. So we will be covering, yet this unit, who is making GLUT4 and who's not making GLUT4. Okay? A lot of you said that insulin gets into the cells in order to do its job. I think that was a physiology thing, wasn't it? Water-soluble hormones don't go into cells to do their job. They do their cells by contacting a receptor, and it's the receptor that then has to do their job. A lot of you said too much sugar in the diet causes diabetes. Okay, and it's actually a matter of look at kilocalories in versus kilocalories out. That's probably the risk factor. Not, you can have a lot of kilocalories that you consume, and the kilocalories might not necessarily be sugar calories. They might be fat calories or protein calories, but as long as you've got that calorie imbalance. So sedentariness, I think you're all, well, people who don't exercise, that kind of offsets the balance too, where you're eating, but you're not burning the calories off. That's a risk factor for diabetes. So this equation, when you eat too many calories and you're burning off, that's a risk factor for diabetes. And it may be that sugar is what you're eating too much of, but it may be that fat is what you're eating too much of, or even protein that you're eating too much of. Okay? And almost all of you associated type 2 diabetes with aging. Okay? And a lot of you also recognize that type 2 diabetes is a growing problem in the United States. But what group of people do you think is growing the fastest? What demographic of diabetes, type 2 diabetes, is growing the fastest? If you look at different age groups, it's growing the fastest in kids. So it's no longer really considered adult onset diabetes. Diabetes, type 1 diabetes is almost always an autoimmune disease where antibodies attack the beta cells of the pancreas, and when about 80% of the cells have been lost, symptoms of diabetes start. Okay? And there's a lot of different ways that you can stimulate antibody attack of the pancreas. Okay. So there are the loss. I'm also thinking from how and what I'm reading that type 2 diabetes also involves a considerable amount of cell death of beta cells. Okay, but we will be covering, we're going to be covering diabetes and insulin resistance every single unit from here on out. Okay. I think it hits every single unit. So I will try to bring up some of the comments that I remember reading about and make some notes and make sure we talk about those. Okay. Thank you all for, thank you. Oh, you know what I was thinking of doing? Is going back and having you, because a couple times I said, well, you should read you should read this statement at the end of the semester, or at the end of this unit. You should all reread your statements at the end of the semester. And I think what I might do is, since I have them, is have you go back and read them. And if you've lost yours, I've got an electronic version of it. Okay? So I'll try to remember to do that. Let's see how you would rewrite that at the end of this semester. Okay, so today we're working on, are there any questions about, I'm trying to figure out how to give you guys credit for it, give you some bonus points on the test or something. I mean, I do, I know just by saying, I really appreciate the fact that you're so diligent. But yeah. Okay, so we wanted to cover membrane proteins today, and probably, what's today? Tomorrow. To make a distinction between integral membrane proteins and peripheral. So the distinction was actually originally chemical, and not at all what did the protein look like in relationship with the membrane. Okay? So an integral membrane protein was kind of defined as a protein that you could not release from the membrane unless you dissolved the membrane. So this was so integral, this protein was so integral to the membrane, you had to destroy the membrane in order to get that protein out. That definition still holds today, but now we think of integral membrane proteins as according to how are they oriented in the membrane. Peripheral membrane proteins, all you had to do is wash the membrane with the salt solution, and you could wash off that particular protein. So it was really not in any way physically attached to the membrane. Leave the membrane intact and just wash off that protein. Okay, so your book shows an excellent slide of what are the orientations of the integral membrane proteins in a membrane, and this is a different slide of the same thing. This one is, for me, the most fuzzy. So here's a protein that is probably made in the cytoplasm, and then because of a change in conformation can integrate into the at least one layer of the lipid bilayer. This is probably a transient membrane protein. And we will encounter proteins that are like this, that sometimes when they're active, they insert into the membrane about like this, and when they're inactive, they're not in the membrane. Single pass proteins, notice that there is a single chain, and it's an alpha helix, and I'll come back to that after we go through these proteins. Okay, and a single alpha helix through the membrane. So part of the protein sticking out of the cell or on this non-cytoplasmic side, and part of the protein's on the cytoplasmic side of the membrane. The insulin receptors are a really great example of a single pass protein. Where on the outside of the cell, there has to be a binding site for insulin. And on the inside of the cell, there's enzymatic activity. This happens to be a kinase enzyme. We'll encounter lots of proteins that are single pass proteins. Almost all of them are going to be receptors for some ligand. Okay, so something's got to bind to those types of proteins. We'll also require, or take a look at multi-pass proteins, okay, that weave in and out of the cell membrane, or the ER membrane, or the Golgi membrane. GLUT4, okay, any transporter is going to be multi-pass. The cystic fibrosis protein has 12 transmembrane domains. Weaves in and out 12 times. I can't remember about the glucose transporter. I'm guessing 6 or 7 times. So here is two proteins that are interacting with each other. Okay, they're both single pass proteins that are interacting with each other to form a complex. This is actually what an activated insulin receptor would look like. And we will see other examples of receptors that really aren't active until they dimerize, until two receptors come together. And they co-activate each other. Okay? This would be a peripheral membrane protein. Its contact with the membrane is actually through a protein, an integral membrane protein. We will see lots of proteins that are peripheral membrane proteins. We probably won't identify that as, oh, here's a peripheral membrane protein. Let's see, we've got a lot that are associated with fatty acids. So the protein itself is not at all interacting with the membrane. But at some point, and maybe we'll have time to cover it today, a lipid group is covalently attached to the protein, and that lipid group pokes into the membrane because that is just a fine way to exist. We'll see lots of proteins. So the proteins in signal transduction that are attached with fatty acid. The GPI anchor in this thing is incorrectly drawn because the GPI anchor is not attached to a protein that's anchored by a lipid is not really attached to the two fatty acids. It's really attached to a whole bunch of carbohydrates that are attached to glycerol. So sometime we'll take a look at that, but that's just wrong. It's just something, your book does a much better job showing a GPI anchored protein. These types of proteins are commonly found in rafts, but probably will never encounter or talk about a GPI anchored protein. So we will see lots of examples of this, lots of examples of this, and this, and this, and we'll certainly come across proteins that are transiently integral membrane proteins. So I want to talk about the alpha helix that you see spanning the membrane. Okay? And notice, I just want to point out that part of this alpha helix is sitting next to the polar heads. Okay? And if on the cytoplasmic side, the polar heads tend to be negative, okay, what do you suppose the charge is going to be on the amino acid arbors? Positively charged. Remember that, because that's going to help you know the orientation of a protein in the membrane. So if I show you a protein that's not oriented in the membrane, you can predict what part of the protein is cytoplasmic, what part of the protein is not cytoplasmic. Okay? Up here, the polar heads tend to be neutral, although there's positive and negative charges on them. So these are, in the purple region, are probably hydrophilic, but not necessarily positively charged or negatively charged.
So would on the outer surface would it be more negative or neutral?
More neutral. So you'd have a hydrophilic amino acid. Or you could have a positive, or you could have a negative. But almost all single and multi-pass proteins have a positively charged amino acid that's associated with the non-cytoplasmic glutathione. Your book doesn't show that in this particular chapter, but that is the key. Kelly, did you have a question?
I was just wondering if you knew what page this was on.
Oh, let me look.
577.
Oh, you're 577? Okay.
It looks similar to this one.
Yeah, and it probably does GPI anchor. Yeah, yep. 573 is on what I have. And what else do you have? Oh, that's even better. 577. So there's a little bit of, so on page 573, they're showing you what you might find in a lipid raft, and you got the GPI anchored proteins, but 577 is actually the one that you ought to be looking at. And on page 577, protein example number 6 is the GPI anchor. So the same things, just a different picture. Okay, I'm going to shut this off. I'm going to remind us of remind us one more time about the peptide bond, okay, and its tremendous hydrogen bonding potential. Okay, and when hydrogen bond components, or peptide bond components, like the carbonyl oxygen or the hydrogen on the amine group, when peptide bond components hydrogen bond to other peptide bond components, okay, so these are peptide bond to peptide bond interactions. That gives you the secondary structure of a protein. And that's all I want to say about that. But a secondary structure is sort of what the characteristic of the localized neighborhood of a protein. So alpha helix is one neighborhood characteristic. And I'm going to draw the alpha helix very schematically like this. Okay. And the peptide bonds create this alpha helix, or help create the alpha helix by hydrogen bonding with other peptide bonds. Okay, chapter 3 will talk a little, can remind you a little bit more what an alpha helix is. I'm not that concerned that you have it completely memorized. Okay, So the hydrogen bonds that are forming don't involve R groups at this point. They're just involving the peptide bond components. Notice that in an alpha helix, the hydrogen bonds that form tend to be fairly parallel with one another, so they're stabilizing forces all in the same direction. It's all stabilizing the alpha helix. So you don't see hydrogen bonds in perpendicular to one another. And we also see this in DNA, where all hydrogen bonds that form are parallel to one another, and so the force is, so they have contributing forces, not competing forces. Okay, this is lovely in a biological membrane. So when the alpha helix finds itself in a biological membrane, there are absolutely no water molecules inside the hydrophobic tails. Okay, so the only peptide bonds that can form are the peptide bonds between or the only hydrogen bonds that can form are hydrogen bonds between the peptide constituents. Okay, so you get maximum number of hydrogen bonds that stabilize the protein. Maximum number of hydrogen bonds within the alpha helix. So it's an extraordinarily stable alpha helix. I think there's about 20 to 22, and sometimes if it's a little tighter, you have a little more compacted alpha helix, and you get up to 24. But there's about, let's say about 22 amino acids from this polar head to this polar head. And every peptide bond is going to be involved in some hydrogen bonding. In an aqueous environment, okay, some of the hydrogen bonds, or the peptide bond constituents, are going to hydrogen bond with water. Okay? That weakens the strength of the alpha helix, because not 100% of the hydrogen bonds that are formed are stabilizing the alpha helix. Some of those hydrogen bonds that form are formed with the water. Helps the alpha helix mix with the water. Okay. So probably the most significant characteristic about alpha helices in membranes is that they're extremely stable. What do you suppose is going to happen to that hydrogen, the stability of that alpha helix, if you disrupt the membrane, dissolve the membrane and release the protein?